this signal? Well, there are two ways. The simple way, you will say x of n equal, and then just you start to write the values of each one. Like at n equal -1, the value is equal 2, so you write 2. Then the value here is 1. At n equals 0, you write 1. And the value here is 0.5, you write 0.5. Then 0.25, 0.25, and so on. That's the way you make like a list here. But you got to mark the position for the element at n equals 0, which is equal to 1. So you underline this element. So that's one way. It's easy. But there is another way. If you want to express as a sum of pulses, you got to express everyone. What do you mean by that? You can write x of n equal. There is a pulse at n equal -1, so the amplitude is equal to, you can represent it as pulse delta n plus 1, because this pulse is shifted towards the left by 1 unit, plus 1 delta n. Why delta n? Because at n equals 0. Then 0.5 plus 0.5 delta n minus 1, shifted towards the right by 1 unit. 0.25 delta n minus 2, and so on. So that's the way we can do it. Well, can we do it at the sum? It looks like sum. Well, to do that, just look at any element here. What's 0.25 represent? 0.25 represent the value of x at n equal 2. Now we don't be confused between n and other things, so just call it k. So if you call this x of k, all right, so that's x of k, where k is equal to in this case. So that's actually x of 2. Delta n minus 2, delta n minus k. So in general, you can write any term like x of k delta n minus k. And k change from -infinity to infinity. That's x of n. In general, you express it as a sum of impulses with different magnitude. Let's check this one. What about at k equal 1? So how you write k equal 1? Okay, you say equal, and there are many elements here. Let's just think about, you write x1 delta n minus 1 plus, you continue after 1, 2, x2 delta n minus 2, and so on. Let's check this one, for example. x1, what's x1? The value of the signal at n equal 1. So at 1, it's equal 0.5. So this element is equal 0.5 delta n minus 1. So that's the way you express discrete time signal as a series or as a list here. Okay, that was important because it helped us in the following topics. The objective was said in the beginning of this video that we need to find the response of a system. That's the input signal, call it x of n, and that's the output signal, call it y of n, and that's the system, and it's going to be assumed linear time invariant system. Great. There is a special case. If the input is unit pulse, like you see here, unit pulse, unit impulse, so the output, which is y of n, we'll call it h of n, and h of n is called as unit impulse response, and most of the time we just will call it the impulse response. What is the value of impulse response? Impulse response will help us to find the response of the system to any input different than the unit impulse. We need some example. Here you go. Look at this example. If you have a unit impulse, so it's located at n equals 0, the amplitude is equal 1, and then let's say that was the output. So we consider this the unit impulse response of the system for 1. If you wish, you can write it like that. 2, that's very 2, and then you have 3 ones, and underline 2 because that's n equals 0. That's h of n. That's the impulse response of the system, which will characterize the linear time variant system. Okay, now using this information, if you amplify the input signal, this one, by 2, the magnitude now is double the unit impulse 2. So what do you expect will happen to the output system? It will be the same. Once you know the response of unit impulse response, you can find the response to any other signal. For example, this is double, so h of or the y of n will be double this one. That was 2 becomes 4, 1 becomes 2. At the same location, there's nothing, nothing shift. Okay, so the output in this case will be equal to h of n, because h of n is the response of unit impulse. Well, let's shift. After we amplify the signal, we shift it by 1 towards the right. So you can express this like 2 delta n minus 1. What will happen to the unit impulse you have? It will be double, because the amplitude will be 2, like this one, and then shifted by 1. What does it mean shifted by 1 towards the right? It means this signal that equal 4 at n equals 0 will happen at 1. That's true, it happened at 1. And nothing here now. Everything, all signals will be shifted towards the right by 1. So that's why it's very important to know the unit impulse response of a system, because you can find the response of any input. Maybe somebody will say, but you're still inputting only one impulse. And the input, not all the time one impulse, could be a group of pulses. Okay, let's just look at this example. If we have one, and you got this one, that's the first input, that's the first output. The first input was unit impulse, so the output will be, in this case, h of n. Can you write h of n? Yes, 2, and then you have 3 ones, underline 2. That's the same example. Great. Now we have this signal that we explained previously, doubled and shifted towards the 1, so it'll be double, everything double. 2 will be 4, but not at 0, at 1, because it's shift towards the right, because as you know, this is delta n minus 1, shift towards the right. But okay, if you have input consist of both signals, it has this red one and the blue one, so the output will be the sum of this one and this one. Why? Because this signal x of n is equal x1 plus x2. x1 give me y1, x2 give me y2, so this signal x1 plus x2 will give me y1 plus y2. Superposition. Why? How can we do that? Because we assume from the beginning this is linear system, linear time invariant system, linear time invariant system. All right, so let's see if we add the both response. You have at 0 nothing, at 0 2, so we'll have 2. At 1 you got 1, at n equal 1 you got 4, 4 and 1 become 5. At 2 you have 1, at 2 you have 2, so you have 3, and so on. You just add, so you can use superposition. So when x equal x1 plus x2, so y of n will be equal y1 plus y2. Well, now we can simplify what we learned from previous slide, that's x of n expressed as a sum, and I remind you it's equal x of k delta n minus k, where k change from negative infinity to infinity. Now to find y, how you find y? Very simple thing. You just replace the impulse delta n minus k by h n minus k. So when you do that, you find the output. So the output is equal the sum of x of k times h n minus k, where k changing from negative infinity to infinity. This formula, or of this summation formula, we can write it like this: y of n is equal x of n conjugated over h of n. That's convolution sum. That's what we call it, convolution sum. That's exactly the same thing that would deal x of k and h of n of k. Let me just remind you, h of n minus k replacing delta n minus k. That's you start by this expression. Okay, great. If you flip x and h, change the position, you can write it h of n times x of n. I can convolute it over x of n. And in this way, the sum will change. Instead of x of k, you'll have h of k. Instead of h n minus k, that will replace by x n minus k. So both ways, they work, find the same result. Let's just see, maybe it looks complicated, but actually when we do numerical example, it will be easy. And before we do the example, I just like to remind you by some signal operations on discrete time signal. That's the question. How to sketch f of minus k and f of 2 minus k. Given first f of n, that was normally given f of n. That's a discrete time signal called f of n, and it's given 1.5, 1, 2. Okay, let's just see what's 1.5. This is 1.5 at n equal -1, because the underline here at 1, it means that's when n equals 0. And then you have 1, so that's 1.5, and that's 1, and then 2, 1.5. That's the signal f of n. Remember, I want to find f of minus k and f of 2 minus k. First, you express f of n instead of n, you do k, f of k. So what happened? It's the same graph, just that's instead of bn, that's k, but nothing happened. I'll put the values here: 1.5, 1, 2, 1.5. Now I want to find f of minus k. You remember in signal operation, f minus k, it means reflection on the y-axis. So that's 0. It doesn't. We don't change it. At 0, it was equal 1. That's at 0, it's equal 1. And then you flip everything. So 1 point. What's the right of 0? You have 2, 1.5. So be 2, 1.5 other direction. What do I mean by that? Just let me make it very simple. When we have f of n, we have it in this way: 1.5, 1, 2, 1.5. So when that's f of k. If you want to make f of minus k, what you'll do, you leave this as it is, and all the thing will be reflected on the other side. Let me just write in space here. So it was like that: 1.5, 1, 2, 1.5. That was f of k. Now I want to make f minus k. I keep this one at when n equals 0, and all the things will be reflected. So you write 2, 1.5. Done. And about this one, go in other direction: 1.5. In this way, you got f minus k. Let's just look at that. That's f of k. So f minus k will be make the reflection. That's what you got. And that's exactly what you're supposed to get. All right. Start with 0.5. That's what 0.5. Yes. And then 1, 2, 1, 1.5. That's f minus k. If you want to move it, if 2 minus k, it means you made the reflection. All right. The inversion for f minus k, and then you add 2. So you add 2 towards the right. What does it mean? For example, the signal 1.5 happened at n equal 1. Now, if you add 2, it will happen at n equal 3. So you move it 2 to the right. So f 2 minus k equal. When you move it 2 units, so what happened? It's very important. Always look for n equals 0. At n equals 0, be 1. The 0 will move to 2, right? It will move to 2. So if you write this thing here, that's now your new 0. This one moved to the right. So who's going to replace it? This signal that was before it or behind it. So when you express it, you will have now, you will write the same thing like this one: 0.5, 1, 2, 1, 1.5. But now Very important. This is n equals 0. It's not n equals 0 anymore. This element will move 2 towards the right. So who is going to replace it? This one. The one behind him by 2. So that will be underlined. That's just simple. You can do it in this way. And of course, the graph help. Why we are learning that? We are learning that because we have here, if you look at the both signal, there is a fun function. We always flip it, n minus k. n minus k. One time we operate it on h, we make h n minus k. And one time we make it on x, we can x n minus k. So in general, we're learning how you do, instead of n, I just pick here a number for n, like 2 minus k. It's the same